Hello everyone. We are here to present our topic CPU schedulers and their types. I am Adamya Jha and my teammates Tanmay Gajbhai and Shrey Kumar will be joining me to explain how CPU scheduling works and why it's an essential part of operating systems. Let's begin our discussion with what a CPU scheduler actually is. What is a CPU scheduler? A CPU scheduler is responsible for deciding which process gets to use the CPU at any given time. Since a single CPU core can execute only one process at a time, multiple processes compete for CPU time. The scheduler manages this efficiently to keep the system smooth and responsive. Good scheduling improves system throughput, reduces waiting time, and ensures all processes get a fair chance to run, making multitasking possible on modern systems. Why CPU scheduling matters? CPU scheduling is vital because it directly impacts how efficiently a computer performs. It helps balance key performance metrics like turnaround time, waiting time, and response time, ensuring optimal operation even under heavy workloads. Without proper scheduling, system would slow down, tasks would queue up, and user experience would drop significantly. That's why smart scheduling is at the core of every operating system. Types of CPU scheduling. CPU scheduling can be divided into two main types, preemptive and non-preemptive. In preemptive scheduling, the CPU can be taken away from a running process and given to another process, usually with one with higher priority or one that has waited long enough. This improves responsiveness and prevents any process from monopolizing the CPU. In non-preemptive scheduling, a process runs until it is finished or voluntarily gives up the CPU, like when it waits for input or output. It's simpler because it can increase waiting time for another process.
Classic scheduling algorithms overview. So now let's discuss four classic CPU scheduling algorithms. First come first serve FCFS. Executes processes in the order they arrive. Is simple but can cause long delays known as the convoy effect. Shortest job first runs the shortest job next, minimizing waiting time, though predicting job length isn't always easy. Round robin. Each process gets a fixed time slice or quantum. It's wisely used in time sharing systems for fairness. Priority scheduling executes higher priority task first, but low priority ones may starve if not managed carefully. Each of these algorithms balances fairness and efficiently differently. Modern scheduler innovation CFS. Modern systems like Linux use the completely fair scheduler or CFS introduced by Ingo Molnar in 2007. CFS focuses on fairness rather than fixed time slices or static priorities. It uses a red-black tree to track each task virtual runtime, a measure of how much CPU time it has received. The task with the smallest runtime, meaning it has been treated most unfairly, runs next. This design ensures balanced CPU distribution and keeps the system responsive for all tasks, from background processes to interactive apps. Scheduling metrics to evaluate performance. To evaluate how effective a scheduler is, we use several key metrics. Turnaround time, total time taken from process submission to completion. Waiting time, time a process spends waiting in the ready queue. Response time, time between a request and the system's first response, crucial for interactive applications. CPU utilization and throughput. These measure how busy the CPU stays and how many processes finishes per unit of time. An ideal scheduler minimizes waiting time while maximizing throughput and CPU utilization.
Real-world analogy CPU such as air traffic control. This slide draws a real-world analogy between CPU scheduling and air traffic control. Just like an air traffic controller manages multiple flights competing for limited runways, a CPU scheduler manages multiple processes competing for limited processing time. Both systems use scheduling techniques to ensure efficiency, fairness, and safety while balancing throughput. They also adapt to changes conditions such as flight delays or system load to maintain smooth operations. Visualizing scheduler impact. This graph compares the performance of different algorithms. We can see that shortage of first usually achieves lowest waiting times. Round robin ensures better fairness, especially for interactive workloads. And completely fair scheduler provides a balance between performance and fairness, making it ideal for modern multitasking environments. In summary, I would like to say that CPU scheduling is the backbone of efficient process management in operating systems. From traditional algorithms like FCFS and round robin to modern solutions like CFS, every approach aims to optimize performance, fairness, and responsiveness. A good scheduler ensures that user gets smooth, lag-free experience even when multiple processes are running competing for CPU time. Thank you for listening.